In this video, we're going to talk about the concept of center of mass. Sometimes called the center of gravity. That's slightly different, but certainly is related. The center of mass is used to determine the center of gravity. But the center of mass is something that most of us have an intuition about, especially if you've played football or some sport in which involved contact. You were probably told at some point to get low. The reason you were told that is because the closer to the ground you can get to your center of mass, the harder it is to topple you over. This is why chairs have what's called a splay of the legs, right? If this is the chair and this is the back of the chair, the chair's legs actually come out like that. They don't go straight down. That's to ensure that the center of mass of this system never gets over one of these endpoints, and that's when the chair falls over. If you've ever seen anybody do a high jump, I'm not going to be able to draw this, right? But they kind of contort their body in this funky shape where they arch their back and go over the bar. What they're actually doing is they're moving their center of gravity around, and so parts of their body are able to get higher than they normally would. So the center of mass or the center of gravity has a lot to do with everyday things. So let's see how to calculate it. Rigorously speaking, if I want to define the center of mass in English, it is that point about which the mass of an object CT, now put in parentheses an S, an object or objects is equally distributed. To this point, when we've talked about motions of objects and collisions, we've talked about them as if they're point masses. But very soon we're going to have to start dealing with what happens to extended objects when they move or they fall or they get struck by other things. Turns out the center of mass has a lot to do with characterizing the subsequent motion. So we need to figure out what it is. So in English, it's that point about which the mass of an object is equally distributed. First thing I would say is it doesn't necessarily have to be inside the object. If you are standing up or sitting down, but you're reasonably straight up and down, your center of mass is somewhere about a level with your navel and almost in the middle of your body. It's going to differ depending on how your body is structured. But if you think of something like a horseshoe, it's a terrible looking horseshoe. The center of the mass of a horseshoe is somewhere about there. Right, it's the point about which the mass is evenly distributed. It's actually probably closer to the U here. About which the mass is equally distributed. There's no point in the body of this thing where you can say, oh, the mass is equally distributed about that point. The center of mass doesn't have to be inside an object. In point of fact, for the high jumper, his center of mass when he's arching his back is somewhere about there. The center of mass actually is underneath the bar, which is how he's able to jump so high. But it's the point about which the mass of an object or objects is equally distributed. As a simple example, imagine two objects of mass, let's say of equal mass, that are some distance apart. Now, intuitively, if they're the same mass and they're equally distant, or not, it doesn't make any sense. If they're this distance apart d, but they're equivalent masses, is what I'm trying to say. Our intuition tells us that the center of mass is, well, in the center of the masses, and it turns out that's right. We're going to show it mathematically in a second, but that gives you some sort of idea of what's going on. Now, this, of course, is a one-dimensional system. If I had other masses put in, I would expect the center of mass maybe to move unless I was very carefully to place them symmetrically. For instance, what if I had a grouping that was not so symmetrical? What if I had, we'll keep this in one dimension. Let's say I have a mass here, and then a mass here, and another mass very close to it. Well, I can't say that the center of mass of the system is in the direct middle of these two masses now. In effect, this has been weighted to the right side. So I have to move the center of mass a little bit towards where it's been weighted. Think about if you've ever been on a seesaw with maybe there was one of you on one side and two of you on the other. It felt imbalanced, right? It felt imbalanced because the seesaw is pivoted at its center. But when you put more than one person over here, you move the center of mass of the system, and so it's harder for this person to do anything but just go up. So how do we characterize this mathematically? Well, if you don't know summation notation, let me introduce you to what it looks like. We know that the sigma means to add some things up. We can also use what's called an index. Usually it's either I or J. Your book is using J. To indicate that this is the index of the object we are adding it. Let me show you what I mean. So the center of mass is equal to this. 1 over, and I'm going to write big M, we'll talk about what that means in a second, of the summation over J of M sub J X sub J. All right, what does this mean? We'll talk about the indices in a second. The 1 over M, the capital M is just total mass. If I have 2 objects, I add them up and get this. If I have 3 objects, I add them up and get the total mass. If I have 37 objects, add them up and get this. So that's pretty easy to see. What about the indices? Well, that just amounts to numbering your masses. Mass 1, mass 2, mass 3. And so what this summation tells me to do is replace J with 1 and then add up mass 1 plus this position 1. We'll talk about that in a second too. Then go back and add to it the second one, M2, position 2. And then go back and add to it M3, position 3. So my index is going to run from 1 to however many objects I have, which I'll call big N. In this case, N would be 3, right? Because I have 3 objects. So this is just the normal notation for how to sum this up. What is this position? Well, it is just that, a position. This implies that you've set up a coordinate system and you have the position of mass 1 for M1. You have M2 times the position M2. You have of M2. You have M3 times the position of mass 3. Let's do a really, really simple one. Let me say that my origin is here. And I'm going to put mass 1 here at a position 2. Centimeters, meters, kilometers, whatever, light years, it doesn't matter, whatever units you want here. I'm going to put another mass of equivalent mass. So this is another M, right, at position 8. Right, and this is my total system. So mass 1 is just M, mass 2 is just M. So this is the same situation I had here, 2 equivalent masses, equidistant. So you might say, okay, I can do this without even messing with the summation notation. The center of the mass is going to be right in between them. If this is at 2 and this is at 8, it looks like the center of the mass is going to be at 5. Let's prove it to ourselves and then get an intuition for how this works. All right, first thing to do, what is capital M? Well, that's just M plus M, mass 1 plus mass 2. It's going to equal 2M. All right, now let's call this mass 1 and mass 2. So now my summation, 1 over M, is equal to summation index from J is equal to 1 to 2, because I only have 2 masses, of Mj xj. I will replace, now this is not right, that should be multiplied, this is center of the mass is equal to this times this, right? Okay, so now let's go back and put in, from this example, 1 over capital M is going to be 1 over 2 little m. And then let's do the summation. Well, the first one, mass 1 times position 1, let's call this one mass 1. That's just M times 2. Again, whatever units you want to have there. m times 2 is my position. My next one, plus, I have to go back and add, that's what the summation symbol tells me to do. M times, what is the position of this? 8. And that's all I have, I just have 2 masses. Okay, well, 2m plus 8m is going to be 10m. So it looks like my center of mass, if I do the math here, is going to be 1 over 2m times 10m. I'm going to lose an m, I get 10 over 2, 5. Just like what I knew it was, right? But this is a simple example of how that works. We'll do a more complicated one and a 2-dimensional one in the next video. And again, there will be units attached to this, whatever units your coordinate system is in. I intentionally didn't put any. It could be centimeters, could be millimeters, it could be feet if you really don't like the metric system. Whatever units you're going to have are going to be here.